Recording it's rolling. It's Monday, April 27th. So last week, I think Wednesday and Thursday, I introduced you guys to the theory of relativity. So I will do a recap with you guys. But it's been a while. This is a pretty wacky theory. Also, I never got to my GPS example, so I'll run that for you guys. And then probably about the second half of class today, I'll hand you guys this page. I'll give you guys, of course, the rest of class today and probably some time where I'm thinking. There's a couple puzzles. On one side, it's the speed of light puzzle. And if you flip it over, on the other side are a bunch of relativity puzzles. And I give you the relativity equations. You guys remember for time dilation and length contraction, right? And then there's a momentum version of it, right? There's also math energy equivalence. You guys know E equals mc squared, the divergent, right? Right, so here, I'll give you guys this later class today, but I'm going to do a recap with you guys first, right? So keep this in mind as I'm doing the recap. When you guys see like, oh, how do you calculate the speed of light? Start thinking about this because this will help you out later, right? Oh, actually, here, I'll give you guys a little hint how this is couched. Okay. So you guys remember this rotating cogwheel here. Right? I have a mirror several kilometers into the distance. Right? I have to tell you some numbers. I told you how far away is the mirror. I told you the diameter of the wheel. I told you the number of teeth on the wheel. Now, there are different versions of this paper, so everybody's like slightly different setups. Okay? But let's say that I tell you what the speed of light is, and my question is how fast do you have to rotate the wheel? That's the actual question on this paper. Now, of course, back in 1849, it was the exact reverse. They were trying to find what is the speed of light, and they would naturally speed up the wheel until everything aligned. Right? But you guys did the opposite. So I'm giving you guys the speed of light right here. Now, one huge hint is, guys, however fast something's rotating, is that called angular velocity? And in this class, if you stick to all base SI units, naturally it would come out to what unit? Yeah, radians per second, right? Radians per second. How fast is something turning? Radians per second, right? Not revolutions per minute, not degrees per hour, but radians per second, right? Naturally in the math. Okay. Now over here, I give you guys a list of questions, and they lead you through one by one, building to, right, the next step, next step, next step. Okay. And there are a few different ways to get to the answer. Probably the fastest way is, guys, look right here and sorry, right here and right here. Okay. So if you can figure out how far this whole wheel turns, which is not very far, right? Might be like a few degrees. Of course, you guys do it in radians, right? How far for the light to bounce back and forth and for a tooth to cover the gap and vice versa. And how many seconds would that have happened in? Now, since you guys know the speed of light, do you guys think you can figure out how much time it takes for light to bounce back and forth? Okay. Which is probably a tiny, tiny, tiny fraction of a second, right? Okay. Yes, if you know how many radians and how many seconds, can you get radians per second? Yeah. Okay. And there's another way you can do this too. If you mark down these questions, there's an alternate way to get there and maybe check your answer. Okay. On the other side are, you guys are going to see these formulas in the recap today. Time dilation, length contraction, got momentum, we got math energy equivalence. And so how do you guys solve these two? And yeah, so in time. All right, so let's do a recap of last week. Oops. Got this going. There we go. All right, so we started with plain Newtonian relativity. We say, hey, what if you had this guy in this lake, this guy in this river? The lake, the water is still, but the current, the river, you're either going with the current, getting a boost, or you're fighting the current on the way back. And you guys remember we ran some time calculations to figure out the guy in the lake is always going to win? Right? It turns out it doesn't matter how fast you make this guy paddle or how fast the river current is, the guy in the lake always wins the race, as long as everything else is equal. Okay, so okay, here's another, plain Newtonian relativity. Sometimes I've heard it called Galilean relativity. Nothing crazy, right? Ball, truck, you can either subtract or add the velocities to figure out how fast you catch. Okay, so that's not crazy, right? All right, then, all right, here's one puzzle you guys have to think deeply on today. So maybe I'll slow down a little bit on this. Is it true that the light would travel to the mirror, but also back? So, guys, if the separation was, for example, 5 kilometers, then what would the two-way travel distance be? 10 kilometers. So, okay, so you really do have to double that distance, isn't that true? That's one thing you guys got to figure out. Okay. And then distance equals speed times time. So it's that travel distance, the travel speed is the speed of light times however much time. Okay. Now, all you're looking for the wheel to turn, isn't that what it is? How many radians it turns? Okay. Is this tooth to cover an adjacent gap? Okay, suppose there's 100 teeth. I'm just making something up. Suppose you have 100 teeth. Aren't there also 100 gaps? Isn't that like 200 things, 100 teeth plus 100 gaps? Okay. And all I want is for the tooth to cover the adjacent gap. So, I meant to ask you guys this too. How many degrees in a circle? Yeah, 360. Right. But more importantly, how many radians is that equal to? 2 pi. So if you take one full revolution, which is 2 pi radians, and divide by 2 times the number of teeth for every tooth plus gap, right? That'll tell you how far the wheel turns during this process. So that by the time this light makes its return trip, there's now a tooth where the gap used to be, so that this observer here no longer sees the reflection of this light. It looks like there's a doorway blocking it. Okay. And then this could be a handy one too. Okay. You guys know how far the wheel turns is equal to how fast it's turning times time. Right? It's kind of like distance equals speed times time, but just applies to turntables. Okay. You can put this all together and get the speed of light. No, this is what you did back in 1849. Now you guys, I'm having you guys do a little different. I'm having you guys solve for this omega here, given that you know what the speed of light is, right? All right. So you'll be doing that later. That'll be all kind of fun. All right, so all right, let's fast forward a few decades. We got Michelson Morley and say, hey, what is the speed of this luminescence ether or Earth's speed relative to it, or what's this relative motion? They think, okay, well, light must travel on on some kind of medium. I know lots of other waves do, and so they were hypothesizing the east-west motion was more like it's paddling in a river, and the up north-south motion is more like paddling in a lake, right? Because of how Earth rotates on its own axis, but also revolves around the sun and so on, right? What they ended up finding was that it didn't matter what time of day they did this or season they always got the two were exactly in phase, right? Which means that light can travel through a vacuum, right? There is no luminiferous ether. So okay, so that's weird. And here's one of the implications of this is that let's go back to a moving vehicle. And these guys pull out their cogwheels and measure the speed of light. They both agree on the speed of light, even though this vehicle's in motion. It didn't work that way for the baseball, but it does work that way for light. Right? Now, Einstein puts this together and realizes, oh, what this really means is that these two guys are perceiving different amounts of time passage. And okay, so if you're inside the train, maybe you see the light just bounce up and down, say that's all it did. But if you're outside the train, say actually it traveled on this diagonal path. Right now, if you take this triangle here, right, this right triangle, you can make a Pythagorean theorem equation out of this, and you can get one guy's time in terms of the other guy's time. So here, this T naught is if you're inside the train, or sometimes called rocket twins time for the twin paradox guy that goes in the rocket. And this green T out here is for someone in an inertial frame of reference who just doesn't move at all. Right. Right. Uh, Now, if you're gonna have a time dilation, you'll also get a length contraction. I walked you guys through a story last week of why that would have to be the case, right? And furthermore, there's a momentum dilation, right? So these are all associated with these, right? Do you guys think later on today, when I gave you guys a page, I gave you guys some numbers, you guys could use these equations to solve for some things? We do that? Right. Oh, and here's the graphical versions of those equations. So this is the exact same thing. I mean, there's the equation right there, but here's what it looks like on a graph, right? And on a graph, maybe it's a little bit different perspective. Guys, are you allowed to ever move through space at the speed of light or faster than the speed of light? No, nothing with mass ever can. Only massless particles can move at the speed of light. Okay? At least on this graph. Okay? Here's a length contraction. You guys remember that one where the train was going through the tunnel? And like, was the train sticking outside the tunnel or was it completely enclosed inside the tunnel? Depends on your frame of reference. You guys remember that? Right. Right. So that could be this one right here. Right. And then there's a momentum version of this momentum. Okay? Here's what Newton predicted. Here's what Einstein says is actually going on. Okay. All right. We've got Minkowski space time. What can affect you in the past and what can you affect it going forward in the future? And then anything outside those green cones is beyond cause and effect. All right, math energy equivalence. Guys, this is the energy of nuclear reactions. So the energy you get out of a nuclear reaction is the difference in mass times the speed of light squared, which is an enormous, enormous amount of energy. Got some equations later on you guys are going to solve to see how much crazy amount of energy is that. Right? There's two different categories of nuclear. There's fission and fusion. The only type we've turned into power plants is this fission. Right? So we've known this since, well, for many, many, many decades, right? Right. Now, for fusion, you get hundreds of times almost 1,000 times the energy going from hydrogen to helium than you do from this reaction on the right. And we can make bombs with this, but we haven't been able to turn this into like a realistic power plant yet. Right. So hopefully a near future technology there. Okay. Okay, we got general relativity. So this is the other half of the relativity story. So Einstein was thinking about this falling man. Says, hey, that would be identical to being in deep space. Or if you're standing on the ground, that really is identical to being a rocket accelerating forward. Right? Like there's no way to distinguish in your local environment between those two scenarios. Right? Which made him think about gravity a little bit differently. So he says, think about gravity being a warp in space-time. And the reason that, for example, the moon orbits the Earth isn't because there's this gravitational force acting as a centripetal force. Instead, the moon is always traveling along a straight line path, but in curved space-time. Okay? And you say, okay, well, great. Well, why distinguish between one versus the other? Right? Because this actually does make some predictions that traditional Newtonian mechanics cannot. For example, the orbit of the planet Mercury, or if you look at, I showed you guys a solar eclipse picture the other day. I think it skewed it to a different part. But anyway, there's a 1919 solar eclipse photo where it wouldn't look like it does with the stars in the background unless you consider it general relativity. Right? Also, lots of observations in the past few decades. Right? So if you look at very distant galaxies, or how do they spin or move away, right? A lot of predictions you can make specifically with general relativity. But there are some weird mysteries. Here are two different mysteries. You guys remember I played you guys a TED Talk last week? Right. So two mysteries out there. Blah, blah, blah. All right. So that is a recap of some new concepts you guys saw. All right. So I gave you guys rest of class today, and I'll see where you guys are by the end of class today on both the speed of light puzzle and also these relativity puzzles.